Okay, in this video is going to be going over a couple of the prerequisite topics for college algebra. So the ones we're going to look at in this video is we're going to do a little bit of review of the different types of numbers. We'll do a little bit of review of order of operations and exponent rules, and then a little bit of evaluating of expressions at the end. So in your homework, I think you got a little bit of some problems where they want you to classify numbers as whole numbers and natural numbers and integers, etc. So the first one we're going to look at here is what we got. We got the natural numbers, and that is going to be your counting numbers. We use a scripted n. So 1, 2, 3, 4, 5, 6, etc. And so the dot, dot, dot usually means that the pattern just continues. The little squiggly lines, that's your set brackets. We'll be using that fairly often in this class. The next thing we'll look at is what's called the whole numbers. The whole numbers are the natural numbers, but also including 0. So that'll be 0, 1, 2, 3, 4, 5, etc. Okay. Next one we're going to look at is what's called the integers, and that is the positive and negative whole numbers. Now the Germans got to the integers, and the German word for numbers starts with a Z, so that's why we have that funny scripted Z. I'm going to write it in the compact notation, but what integers looks like if we wrote it out is it'd be dot, 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 -3, -2, -1, 0, 1, 2, and 3, and etc. So that's what it's going to look like. So if we want to write it as a list, we're going to write it as 0 and then plus minus 1, plus minus 2, plus minus 3, and etc. Okay. So 0, plus minus 1, plus minus 2, plus minus 3, and etc. Okay. Oh, and so it looks like I do it again. Okay, so anyways. Next type of number we're going to look at is called the rationals. And that's going to be any type of number that can be written as a fraction. We use a funny scripted Q for quotient, and that's going to be the set of A over B, where A and B are integers, and that funny looking E means element of or lives in, so that lives in the integers. And not A, it should be B. There we go. And B is not 0. Okay, so thou shalt not divide by 0. We'll do a couple examples of what integers might look like. So not integers, excuse me, what rational numbers would look like. So 1/3 is a good rational number. The number 5 is a rational number because it's a fraction. We could write it, well, it's not a fraction, but we could write it as a fraction, as 5 over 1. So 5 is a fraction, it's a rational number. Any sort of repeating decimal like 0.11111, or a terminating decimal like 0.75. So any repeating or terminating decimals are also rational numbers. Okay, or I could also do -5 as a rational number. Okay. Now, every natural number will be a whole number, every whole number will be an integer, and every integer will be a rational number. So we have sort of a hierarchy there. Not every whole number is a natural number because 0 is a whole number, but 0 is not a natural number. So you got to be a little bit careful there. Okay, the next type doesn't necessarily fit this hierarchy. It's called an irrational number. And those are numbers that cannot be written as a fraction. So there's no way we can write them as a fraction. And we'll look at a couple of common examples of what irrational numbers are going to be. So an irrational numbers are numbers that cannot be written as a fraction. So for example, probably one of the most famous ones is pi. So pi is approximately 3.14159, etc. Now the etc. there doesn't mean the pattern repeats. It's a non-terminating decimal. E, Euler's number, we'll be dealing with that later on in the semester. That's about 2.71. And then any square roots, we'll just stick with square roots for now. Any square root of a non-perfect square is irrational. To giving it an example of a rational, or in fact a natural number that has a square root. For example, the square root of 36 is 6, so that's a natural number. Okay. Now the real numbers, we'll use the scripted letter R. Can be also written as an interval of negative infinity to infinity. And that's all the real, well, not all the real, it's all the rational and irrational numbers. So the real numbers is all the rational and irrational numbers. And then finally we have the complex numbers, and they use a funny scripted C with a slash through it. And that's going to be the set of all A plus BI, where A and B are real numbers. Okay, and then where I squared is -1 and the square root of -1 is I. So we'll do a little bit more with I a little bit later, but hopefully you got a little bit of familiarity with I. And let me give you a couple examples of what some complex numbers look like. So example 5 minus 3i, that's a complex number. 5 is the real part, and then -3 is the imaginary part. -4 is also a complex number. Any number is going to be a complex number. And how we can write any number as a complex number, like -4, we can say it's -4 plus 0i. Okay, or 2 plus 4i over 3, that would also be a complex number. Now if we go back to -4, -4 is the real part, and then there's no I, so we say 0 would be the imaginary part. For a fraction, the real part would be 2 over 3, and the imaginary part would be 4 over 3. Okay, so that's the first part we're going to look at. Next part we're going to look at is a little review of order of operations. So you might have remembered PEMDAS, or please excuse my dear Aunt Sally, or something to that effect, to kind of remember the order of operations. But we have to be a little bit careful about the multiplication, division, and then addition and subtraction. So the order of operations says to go ahead and do the stuff inside the parentheses first. Then we'll look at the exponents. And then we're going to do multiplication and division in order from left to right. So multiplication and division in order from left to right. And if we don't follow this, then we're going to get a different answer for the same problem. We don't want that. That's no good. Okay, so for example, 5 divided by 5 times 10. The correct order of operations is to do the division first, because we see the division first. So we'll do 5 divided by 5, which is 1, times 10 is 10. Now if we do it the other way, we would have 5 divided by 5 times 10, and if we did the multiplication first, we'd have 5 divided by 50, and I think that's going to be 0.1. And that's a problem, because we're getting different numbers for the same, or different answers for the same problem. So we don't want that. So this is our agreed upon method of working out something like this. And we have a similar problem with addition and subtraction. We got to do it in order from left to right. If we change that, then we're going to get a different answer for the same problem. So addition and subtraction in order from left to right. Okay, so if we, it said 10 minus 3 plus 7, the correct order would be to do the 10 minus 3, which is 7, then add 7, we get 14. If we do the other order, 10 minus, if we do the -3 plus 7, then it's a little bit dubious in terms of what we do. Is it -10, +10? So 10 minus 3 would be 7, and then 7 plus 7 is 14. That's the correct order. But if we combine these and I get -10, that's a problem, because then I'm getting a different answer for the same problem. So we don't want to do that. Okay. So simplify means a lot of different things. Usually it means to kind of combine like terms, reduce fractions, and to that effect. And so we're dealing only with numbers here, so we're going to go ahead and combine our like terms, and in order to do that we need to follow the order of operations. There are no parentheses here, however we have a 6 squared, so we're going to go ahead and do that exponent first. 6 squared is 36. Plus 9 and then minus 33. Now all we have is addition and subtraction. We have to do that from left to right. We see the addition first. We do the 36 plus 9 is 45. And then minus 33. And then that's the last operation to do the subtraction. And we get an answer of 12. Okay. So we'll go through, we'll do a couple more examples. Let's see what we got now. So number 2, I think we got a fraction here. So negative 1 plus 3 squared minus negative 6, all over negative 4 plus 5 minus 6. Okay, so for like this type of problem, if it's a fraction, you can kind of think of it as 2 separate problems. Work out the top following the order of operations, work out the bottom following the order of operations. Okay, so the top there, we can go ahead and square the 3 and we get 9. So we've got negative 1 plus 9, and then we have minus a negative 6. And so think of it as subtracting a negative or taking away a negative, so that's actually a good thing. So when we subtract a negative 6, what's going to happen is the minus sign and the negative sign are going to offset, and we're going to get a plus 6 there, addition. On the bottom there, negative 4 plus 5 is 1, and then minus 6. Okay. On the top, negative 1 plus 9 is 8, and then plus 6, all over negative 5. And so that's going to give us 14 over negative 5. Okay, that's fine. You can bring the negative to the top, or you can put the negative in front of that. I'm okay with any of those. Whether you're using MyOpenMath or the Lumen Online Homework Manager, they'll both accept both of those. I'll accept both of those I'm sorry, not both of them, all 3 of them. Typically, we put the negative in the front of the fraction, like we have here, or kind of on the top there. That's usually what we do. It's not wrong to have it on the bottom there, but usually the convention is to put it in the front or on the top there. Okay, moving along, let's look at number 3 here. So we got some fractions. So 1/3 plus 5/6 in parentheses times 1/2. And there's a couple of ways of approaching this. You know, you're probably familiar with the distributive property. That would be around. We're going to go ahead and just follow the order of operations. So we're going to add 1/3 and 5/6. To add fractions, we do need a common denominator. So we're going to find the least common denominator of 3 and 6. Since 6 goes into 6 and 3 goes into 6, that's the common denominator. So the 1/3, we need to multiply it by 2 over 2 so that we get a denominator of 6 plus 5/6 times 1/2. Okay, so that's going to be, so when we multiply fractions, it's just straight across and straight across. So the 1 times 2 is 2, 3 times 2 is 6, plus 5/6 times 1/2. Now once we have a common denominator, we can go ahead and add the numerator. So 2 plus 5 is 7, keep the denominator of 6, times 1/2, and then multiply your fractions straight across, straight across. Okay, so 7 times 1 is 7, 6 times 2 is 12. Okay, I think we got one more example of the order of operations here, and then we'll get going on to some exponent review. Okay, so we got one more here with some exponents here. So we got 4 plus 2 quantity squared minus 4 squared plus 2 squared. And so 4 plus 2 is 6, quantity squared. We can go ahead and square the 4 and the 2. They're kind of their own thing. They're separated by the subtraction and the addition, so we can be a little bit more efficient here. So we got minus 16 and then plus 4. Square the 6 to get 36, minus 16 plus 4. 36 minus 16 is 20, plus 4. And that's going to be 24. Okay. I did want to make a comment or two here about, you know, squaring or cubing or something to that effect, or a note here with a negative. So if I say negative 2 squared, okay, the negative is on the outside, which means it's not being squared. So the only thing that's being squared is the 2. So the negative stays on the outside, and then you got 2 times 2, so that's going to be negative 4. If we want to square the negative, we put parentheses around it. So you put parentheses around anything that you want squared. But if it's just, like that, 5 squared, that means 5 times 5, 25. If we say like 3x to the fourth, for example, that's it. That 4 only applies to the x. If we want to make it apply to the 3 also, we'd put parentheses around that, and that would be 81x to the fourth. So we got to be a little bit careful there. So when I do negative 2 quantity squared, it's going to be negative 2 times negative 2, which is going to be 4 there. So we got to be a little bit careful there about parentheses and squaring and whatnot. Okay. So we're going to look at the exponent rules, and if you have my handout from Blackboard, I have all the rules listed, and then I got, I don't know, 6 examples of doing that. I might throw in another example or 2 also. So I'm going to integrate those examples in with each one. So we'll do a product rule, and then the example of product rule, quotient rule, etc. Okay, so we're going to look at our exponent rules, and so we're going to be using the letters A and B, and we'll go ahead and make the assumption that A and B are not 0, and then M and N are going to be our exponents. Those are going to be real numbers. So the first rule we're going to look at is what's called the product rule, and so if we multiply B to the M times B to the N, when I multiply like bases, I'm going to add the exponents. So B to the M times B to the N is B to the M plus N. Okay, so here's example number 5. 4 squared times 4 to the 7th. We'll go ahead and multiply that, and that'll be 4 to the 2 plus 7, which is 4 to the 9th. Notice I didn't multiply the 4 times 4, so I don't want to do that. I don't want to do the multiplication first before I do the exponent. So using this product rule is ensuring that we do the exponent before we do the multiplication. Now 4 to the 9th is a pretty big number, so we're going to go ahead and leave it there. You can use your calculator to figure it out if you like. Okay. Now the quotient rule is going to involve a quotient or a fraction. So that's going to be B to the M divided by B to the M, and you're going to subtract your exponents. So it's the top exponent minus the bottom exponent. So B to the M divided by B to the N is equal to B to the M minus N. So you subtract your exponents. Example number 6, Z to the 20th over Z to the 4th. It's going to be Z to the 20 minus 4 using your quotient rule, which is going to be Z to the 16th power there. Okay. Next rule we're going to look at is what's called the power rule. And if I have an exponent raised to an exponent, you're going to multiply the exponent. So B to the M raised to the M is B to the M times N. So for example, if we have Y raised to the C raised to the D, that's going to be Y raised to the C times D. 0 exponent we'll see quite a bit too. And that is B to the 0 is going to be 1. And I can give you kind of an argument for that. So, for example, 1 is the same thing as 5 over 5. And that's the same thing as 5 to the first power over 5 to the first power. Using the quotient rule, that would be 5 to the 1 minus 1, which would be 5 to the 0. So then I'll give you a little bit of an argument of why the 0 exponent is, in fact, 1. Okay? So, for example, if I have 125, A, B, C, D, E, F, G, all raised to 0, that's just 1. That's just 1. Now, I'll go ahead and make a comment here. Let's say I have negative 9 to the 0 power. That negative is on the outside. The negative is not being raised to the 0 power. So only the 9 turns into a 1. You still have the negative outside there. However, if I want to raise the negative also to the 0 power, I put parentheses around it. And so all of that turns into a 1 there. So you got to be a little bit careful there about any sort of exponents and negatives. So if we want to do the exponent to the negative, you got to put parentheses around it. Okay. And I think I'm going to do an extra example or two for some of these exponent rules here. So for example, we're going to look at the negative exponent rules. And a negative exponent just means it tells you to change locations. So b to the negative n is the same thing as 1 over b to the positive n. And 1 over b to the negative n is the same thing as b to the positive n. So you just change locations from numerator to denominator if you have a negative exponent. Okay, so an extra example of this, I think we're going to do 2 of them. So let's say, for example, I have 3 to the minus 2. That's going to be 1 over 3 to the positive 2, or 1/9. Or what if I have 1 over 5 to the negative 2? That's going to be the same thing as 5 to the positive 2, which is 25. The next thing we're looking at is power of a product. So if I have AB raised to the n, we can quote-unquote distribute the n power. We have to be a little bit careful with it. So this is going to be a to the n times b to the n. Okay, and so we'll do an extra example here. So 3x squared raised to the 4th power, that's going to be 3 to the 4th power times x squared to the 4th power. 3 to the 4th means 3 times 3 times 3 times 3, and that's 81. And then x squared, and then raised to the 4th power, you're going to multiply the exponent, so that'll be x to the 8th power there. Okay? All right, we got fraction raised to a negative exponent. We'll also look at the radical notation. So if I have a fraction raised to a negative exponent, what that's going to cause us to do is to flip the fraction over. So we'll see what that looks like generically. So we have a over b raised to the negative n. That's going to be the same thing as b to the n over a to the n. Okay. So let's go ahead and see what that looks like. We'll do an example here. So 2x over 7y squared, and then raise the negative 2. We'll go ahead and flip the fraction over. Okay, so 7y squared over 2x, all that squared, and then that'll be 7 squared, y squared squared, 2 squared, and x squared. So we'll just apply that exponent of square to everything. 7 squared is 49. Y squared squared, you're going to multiply the exponents, y to the 4th. 2 squared is 4, and then x squared. And then we could check to see if there's anything to reduce. If there's nothing, we'd leave it at that. Okay. And then the last thing we'll look at is the radical notation. So the nth root of b to the n is the same thing as the nth root of b and n quantity raised to the n power. As a rational or fractional exponent, that is b to the m over n. So the root is going to be the denominator when you convert to rational. Okay. What we'll see most commonly is the square root and the cube root. So commonly used. The square root of b is the same thing as b to the 1/2 power, and the cube root of b is the same thing as b to the 1/3 power. We'll see that all the time, so it might be something that you want to make note, highlight, or whatever, because you'll see it all the time. All right. So what if we have 27 raised to the negative 1/3? Okay. Well, the negative exponent just says, okay, send it to the denominator. So 1 over 27 to the 1/3 power. 1/3 power means cube root, so that'll be 1 over the cube root of 27. And what that's asking us is, if I cube something, what do I cube to get 27? Well, that's going to be 3. 3 to the 3rd is 27, so therefore the cube root of 27 is 3. So 1/3. Okay. The last thing we're going to look at is evaluating some expressions. And what we do there is they'll give us some values for a, b, c, whatever, or maybe x and y. They'll give us an expression, and you just got to plug those numbers in. And it's basically an order of operations problem after you plug in the numbers here. So we're going to evaluate a is 8, b is 6, c is 3, d is 4, and e is -2. And we'll do 2 examples of evaluating. So number 11 here, a times the quantity b minus c squared over d. So we just got to plug in all the parts and then evaluate. So A is 8, and then 6 minus 3 squared over 4. So it's going to be 8 times 3 squared over 4. Do the exponent. 8 times 9 over 4. So that's going to be 72 over 4, which reduces down to 18. Okay, and one more example. 5 raised to the e power. That's 5 raised to the negative 2 power, because that's what e is, which means 1 over 5 squared because of the negative exponent, which is 1 over 25. Okay, so this was a very brief review of some prerequisites that you'll need for college algebra. The homework assignment will reflect a lot of what we talked about, so you can practice that. You can go ahead and read through sections 1.1 and 1.2 in the OpenStax textbook if you're looking for more examples. And as always, you're more than welcome to send me an email with any questions you have. So we'll see you next time.